All right. Hello, everyone. My name is Alan Meadows. I'm a cloud architect at AT&T. We're going to be presenting OpenStack-Helm, the ideal solution for telcos. And I'm also here with
Pete Burley, cloud architect at Accenture.
Madhukar, Contrail team at Juniper Networks.
All right. So briefly, just our agenda. So first, we're going to just briefly describe what is OpenStack-Helm. Secondly, how is it used at AT&T? We're obviously a telco, so there's some relevancy there. And also, we're going to touch upon the enterprise-grade maturity within OpenStack-Helm. And after that, we're going to go into OpenControl in terms of where they are today, where they're going, and also how they're integrating with OpenStack-Helm. And then finally, they're going to do a demo for us, an OpenControl demo, upgrading and running VNF within OpenStack-Helm.
A live demo.
A live demo. Sorry. So briefly, a little bit of the history on OpenStack-Helm. So it started as a discussion at the Barcelona OpenStack Summit. The next phase was an open source proof of concept in the AT&T repository in November of 2016. We brought it to OpenStack in April of 2017, and I'm really happy to report that it's an official OpenStack project as of October 2017. So I think really before we get into OpenStack-Helm, it's always really relevant to point out what is Helm, especially for those in the room who need a little bit of background. Most simply put, Helm is a package manager for Kubernetes. It helps you define, install, and upgrade even the most complex Kubernetes applications. It uses Helm charts, and these charts are a collection of files that describe a related set of Kubernetes resources. Helm wraps up each of these charts into a concrete release, which is a tidy little box that's a collection of all Kubernetes resources that compose that service. So you can interact with that release as one unit, whether to install it, upgrade it, or delete it. And at its core, the value that Helm brings to us in OpenStack-Helm is allowing us to templatize our experience with Kubernetes. It provides a standard interface for operators or high-level software orchestrators to control the installation and lifecycle of Kubernetes applications. So that brings us to what is OpenStack-Helm. So OpenStack-Helm is a marriage of Kubernetes, Helm, and OpenStack, and seeks to create Helm charts for each OpenStack service. So these charts provide complete lifecycle management for these OpenStack services. Users of OpenStack-Helm either deploy individual OpenStack components along with their required dependencies, or all of the OpenStack components that we have Helm charts for. It heavily borrows concepts from Stack-and-Eddies and other complex Helm charts. And ideally, at the end of the day, this project is meant to be a collaborative effort that brings OpenStack projects into a cloud-native model. So what is our mission with OpenStack-Helm? I think this quote up on the screen sums up the overarching vision that we have pretty nicely. The OpenStack-Helm project provides a framework to enable the deployment, maintenance, and upgrading of loosely coupled OpenStack services and their dependencies individually or as part of complex environments. There's really a lot in that mission statement if you unpack it. We're essentially stating that we want to streamline the process of standing up OpenStack as an application within Kubernetes. But not only that, we want to ensure that we're enabling those updates and upgrades and their dependencies, whether those are infrastructure services or OpenStack services, such as in infrastructure services, example of those are things like MariaDB, Ceph, and so on. And finally, we want to ensure that we provide the operators the capability of maximum configuration flexibility, while at the same time choosing as few or as many of the OpenStack ecosystem components that they want to deploy, with no pre-baked assumptions of what those services might be. And so at this point, I'm going to hand it over to Pete to go a little bit deeper on the internals.
Okay, thanks, Al. So one of the early decisions we had to make with OpenStack-Helm was how we wanted to structure these charts. And as we were starting from a clean sheet of paper, we were able to take a step back and really sort of consider what is OpenStack. And we believe quite strongly that rather than a single application, OpenStack should be considered as a suite of as-a-service components that can be combined as desired to meet a particular enterprise's needs. And we tried to capture this in the mission statement that Alan introduced. And in contrast to many complex application deployments using Helm, the path we chose for OpenStack-Helm was an independent chart approach, which essentially means that every chart is self-contained and independent, and their installation results in a single Helm release for each component installed. And from an operator perspective, this is really important to us, as it provides sort of a real certainty that when we want to upgrade or configure a particular component, we will only be affecting that component in isolation. So in some ways, you can almost view a Helm chart as a container for an application suite. And many tools have been developed to extend Kubernetes, which enhance it to sort of deal with complex workflows. But we chose to push all control to the edge by embedding the orchestration logic for a process within a pod itself, which is the atomic unit of deployment within Kubernetes. And this approach lets us capitalize on the simplicity and robustness of the native primitives that Kubernetes provide us with to produce a solution that is both highly scalable and resilient. So, how does this look in practice, and what does it mean for developers and operators of OpenStack-Helm application deployments? I think there's quite a lot up on this screen, but if we just look at the picture on the side here, we can see one of the great things about the early interest in OpenStack and Kubernetes was that there is a real catalog of design patterns that have been proved out by the various projects. And we capitalized on that quite liberally by taking aspects as we saw fit. So we took Kubernetes entry point from Stackinetes, the layout of SAP's early work in packaging OpenStack within Helm, and the idempotency and init container model from Harbor. And as much as possible, we used common patterns throughout the structure of our charts, building on the base declarations of the default values, requirements, and other things embedded within the chart YAML and values YAML to provide metadata about a service. And to retain the loose coupling of the services, we only use the requirements YAML to declare a single dependency, which is common throughout all of our charts, which we refer to as Helm Toolkit. And Helm Toolkit itself does not deploy a single Kubernetes object, but is analogous to a software library for Helm charts, containing GoToPL lookup functions for endpoints and other helpers, common patterns that we deploy throughout our charts and Kubernetes objects, and management scripts for instantiating services. And this allows us to abstract much of the complexity away from developers, significantly reducing the barrier for entry to the project for people looking to contribute or reuse these patterns that we've developed. And within that, the chart contains sort of some fairly common primitives that make up a service. As I touched on, services and jobs for creating databases and then migrating the schema to the desired version, jobs for user and endpoint management within OpenStack, and specific service jobs to do things like create storage pools for Ceph or set up other infrastructure. And finally, leading on to the application deployment itself. And the last point I'd like to sort of elaborate on further is we try and treat containers in our environment as dumb binary buckets and inject all of the configuration and initialization scripts required to operate it at runtime, which is dynamically generated from either the defaults and the values YAML or operator-supplied overrides. And by doing this, we let people take full control over the project without needing to fork it, which allows us to produce a project that hopefully works for us as a telco and also other users at any scale they wish to deploy. And the other major advantage is we also become agnostic towards the source of image we use and developed with both Loki and Cola OpenStack images as a result. Okay, Alan?
Thanks, Pete. So quickly, a little bit of an introduction on AT&T's actual cloud deployments before we jump in on how we're actually using OpenStack-Helm. So today we have 80 production zones and 100,000 cores within OpenStack spread across 10 countries. So there's a lot of scale there. Each of these zones supports carrier-grade workloads. They're complex deployments supporting anything from common IT workloads to virtual network functions. We have a varying degree of site types, ranging from small to medium to very large site types with hundreds of nodes. And our goal is to be able to support 4,000 compute hosts within a single region. And finally, these nodes have greater than 99.9% uptime available today, and we're always looking to improve that. I think it's worth touching a little bit on the edge cloud stuff. There's a lot of stuff being talked about here at the summit. There's even a special discussion the OpenStack Foundation recently had in San Francisco about this. It's worth pointing out because this is going to be the next phase of AT&T's cloud deployment needs, which was also a driver for us to adopt Kubernetes-based OpenStack deployments. At over 80 regions, we're already demanding fast, predictable deployments and updates, and the edge simply pushes that need even further. So with over 200 deployments being targeted initially, this means we need a way to fully automate with absolute predictability our OpenStack environments. And not only that, the edge environments are typically very small, sometimes as small as several hosts. And that means if we're going to manage resources within OpenStack, the control plane has to be quite thin. A Kubernetes-based OpenStack installation allows us to reduce the physical footprint required to run OpenStack by an order of magnitude, and our ability to build in OpenStack-Helm allows us to pick and choose specific OpenStack services that we want to deploy in those regions. And that was also critical for us given the resource constraints there. These edge clouds will drive all sorts of innovation, from virtual reality to self-driving cars, essentially anywhere where throughput needs are high and latency needs are low, or rather, I should say, where low latency needs are relevant, and that's an exciting place to be for OpenStack, I think. So what do these cloud layers look like in an AT&T installation? So given all of these diverse regions, both large and small, I wanted to touch on how we manage all of these OpenStack installations and how OpenStack-Helm fits into that. So under the hood, we've developed what we call an archipelago of open source undercloud components, which we've nicknamed the UCP, or Undercloud Platform. These help us manage sites from their creation to minor updates through major upgrades, and finally, major uplifts such as OpenStack upgrades. They also help instantiate a base set of infrastructure facilitating logging, monitoring, and alerting. We manage all of these components exactly the same way as we do OpenStack itself, through the use of containers, Kubernetes, and Helm. Effectively, we describe the UCP as our ideal way to manage and release software quickly, with minimal disruption to our workloads, and with absolute predictability. And OpenStack is a part of that complete software stack for us. I want to mention the reason to call out these other components as pertinent to OpenStack-Helm conversation is that we feel it's relevant to describe how we arrive at a working OpenStack-Helm installation in an empty data center environment, and how OpenStack-Helm is really a part of that larger ecosystem for us. So what does the life cycle look like at AT&T for OpenStack-Helm and also other changes into these regions? The lifecycle approach we built for OpenStack at AT&T will leverage all of these UCP components mentioned on the last slide, and OpenStack-Helm fits into that approach really nicely for us. Our front door to each of these regions is a component we call Shipyard, which effectively, and by the way, I neglected to mention, all of these components are open source components. This component that we call Shipyard, which effectively orchestrates all of the other UCP components. The entire site definition is declared in YAML manifests from each of the bare metal hosts that run in that site, including the Helm chart definitions in the form of Armada manifests. And whether we're adding a new Helm chart, a new bare metal server, or simply changing a configuration override or container version, the entire updated manifest is sent to the site via Shipyard, and each undercloud component understands how to calculate its own relevant deltas. If there are any changes, they're processed by that component. And for OpenStack, most of this is driven by Armada, which allows us to declaratively define the Helm charts that we want to instantiate in the site and the environmental overrides that are applicable to that particular environment. OpenStack-Helm allows us to fit OpenStack really nicely into that approach, and any changes to these Armada manifests, which are simple declarative YAML documents, trigger either configuration updates, container image changes, or even entire OpenStack upgrades. The beauty of this system is that all of these changes function exactly the same, move through the graphic up on this slide exactly the same way, giving us one well-tested and predictable process for change. So at this point, I'll hand it back to Pete to discuss our development workflow at AT&T for OpenStack-Helm.
Okay, so For us, using Kubernetes has really sort of changed the way we're able to tackle OpenStack development, as developers can deploy the same thing in a development or a CI/CD environment that they're then really wanting to move into production. And this has allowed us to sort of adapt our tooling there so that we can run the same gates, as I touched on a talk previously today, in the community as we do with modification internally or to aid developers, which really helps speed up the rate at which we're moving. Furthermore, this means that teams from multiple companies can work on the project simultaneously with minimal conflict, which is partly driven through having separate charts for each individual service. And as we change a part of our deployment code, say something like Nova, we can really simply test that in isolation from the rest of our environment, so that compared to a tool like DevStack, we can really sort of capitalize on having a production-like back end sitting behind things, which kind of highlights some of the maturity that we're moving towards.
Finicky clicker. So some of you may have watched Saurabh's keynote that we did this particular summit discussing a next generation OpenStack, and one of the major drivers for the initial development of OpenStack-Helm was providing a way to deploy OpenStack on top of Kubernetes, but it wasn't really the only one. So for us at AT&T, the effort has also been a way for us to drive some of the security, simplified operations, and hitless upgrade requirements into a flexible framework that could deliver a speed predictability for OpenStack installations and changes. On the security front, because this is generally very specific to the organization's own needs, OpenStack-Helm doesn't try to provide a rigid solution here, but instead provides a flexible framework out of the box to drive container-specific security to the operator's own requirements, while seeking to still, though, adhere to container security best practices and limiting the privileged surface area. In terms of operational simplicity, I think we've made great strides in making it both simple to install and lifecycle manage OpenStack itself using this framework. A lot of the OpenStack-Helm mechanisms helping to make this reality, Pete touched on in this talk. And finally, in the keynote, we demoed showing both upgrading OpenStack, and essentially we're not only trying to make upgrading OpenStack a first-class citizen, but also rolling back OpenStack. And to be sure, the effort up until this point has been substantially around the core of OpenStack itself. A thought here that we think is really relevant is we can't ignore the fact that truly achieving a hitless upgrade for the end users of platforms requires that we take along the underlying infrastructure and all of the dependencies that OpenStack has down the exact same path that we're working on here today. Given that our goal at AT&T is to containerize every aspect of our control plane, whether that's Ceph, Contrail, or any other control plane infrastructure element, and lifecycle it as exactly the same way as we do through Helm, the next challenge will be applying the same effort to these services to ensure they can also perform non-impacting upgrades, just like we're trying to achieve for OpenStack. So to talk a little bit more in detail on how OpenControl is trying to solve that challenge, Madhukar from Juniper is going to discuss their approach at integrating OpenControl into OpenStack-Helm and their upgrade efforts on that front.
Thanks, Alan. So let's just talk about what OpenControl is, right? So OpenControl is an open source SDN platform built using standard-based protocols. So OpenControl control plane is a logically centralized, physically distributed control plane with a distributed data plane implementation. So the first thing we talk about is orchestrators, right? So OpenControl supports various orchestrations, including OpenStack, VMware vCenter, Kubernetes, and Mesosphere. So all these orchestrators, like the Neutron plugin, for example, let's consider OpenStack as an orchestration. So where we have a Neutron plugin, so Contrail controls resources are exposed using a REST API, and those orchestrator plugin uses those REST API to create objects in the Contrail controller. So Contrail controller comprises of three components: config, control, and analytics. So config is the place where we kind of create all the resources, and config is also responsible for converting those high-level objects into low-level objects. This is where the controller will kick in, and he will basically make sure that he's going to propagate those low-level objects information to the vRouter using a standard XMPP channel. So vRouter is located in all the compute nodes, and it is coexisting with the hypervisor. So basically, OpenControl is a overlay-based solution, and vRouter is the one who is responsible for establishing those dynamic tunnels. OpenControl supports various encapsulation methods to establish the tunnels, like MPLS over GRE, MPLS over UDP, and VXLAN. Control controller speaks to the external, like it could be anything, internet, using the SDN gateway. So it peers with the SDN gateway using BGP protocol. So this is how the overall OpenControl architecture looks like. But what we want to achieve out of this OpenControl architecture is nothing but a logical view, right? If you see on the right-hand slide. So there is a blue virtual network, and there's a right virtual network. And we want to steer traffic from blue virtual network to the red virtual network using some service instances. It could be anything like a virtual firewall, a virtual load balancer, or any other network, or any other VNFs. So early this year, what we have done is we have containerized our Contrail services. So we can say it in two parts. One is the control plane. So we have basically divided it into 3 containers: analytics, analytics DB, and controller. Whereas controller is hosting the config and control both the components. When it comes to the compute node, we have vRouter agent container, which basically helps to insert the vRouter kernel onto the compute node. And also it runs the agent process itself. So this is how our OpenControl container looks like. And all of these containers are publicly available to download using the Docker Hub. Okay. So this is pretty much the same slide which Alan showed. What we have done is we have added an OpenControl logo to it. So what we want to convey using this slide is we are pretty much using the same utilities and all the implementation of OpenStack-Helm. And what we are doing is we are just using the charts to manage the cluster lifecycle of OpenControl using the same charts. And that's what we wanted to show as part of this demo. Okay, so it's been few months. We have been collaborating with Alan, Pete, and OpenStack-Helm team. And we got a lot of very good feedbacks. And today, with the charts which we have and the charts which will look like 3 months back, it's completely drastically different, right? And we think that we pretty much are aligned with what OpenControl design charts looks like, right? So it's very simple, like the one which Pete was showing before. So basically, it has configuration. The control, basically all the charts of OpenStack-Helm has 2 config maps, which is etc and bin. So etc hosting the configuration files required by the controllers, and binaries are nothing but some scripts which are been stored in the config maps. It could be used for any purposes, like readiness checks, liveliness checks, and creating few resources, instantiating few services. That could be done using those binary config maps. So what we have done is we have created 2 charts. One is OpenControl controller chart, and another is OpenControl vRouter chart. It has, as we said, it has 2 config maps each, etc and bin. And these charts are going to install, like OpenControl controller chart will install the controller pod, analytics pod, and analytics DB pod, whereas the vRouter chart will install the vRouter agent container. So this is the usual flow of an operator will use to create a virtual network or a VM or anything using the Horizon UI. So what we want to highlight is how we have integrated OpenControl with OpenStack-Helm charts, right? So as you can see, there are 2 red boxes, which are the major changes what we did. One is with the Neutron plugin, and another is with the Nova Compute and the libvirt. So it's so simple to integrate any kind of software to the OpenStack-Helm. For example, what we did was we created our own container for Neutron server and also for Nova Compute. And what we had to do was the major changes were just in the values.yaml file, and all the configuration changes, we just need to mention that that this is the driver. For example, OpenControl is the driver which you need to point to. And we did minimal changes to the templates itself, and we were able to successfully complete the integration by just changing the neutron charts and the nova charts. So that is the power of what OpenStack-Helm brings. You can easily, it's very pluggable, and you can just do minor changes, and you can get it integrated with OpenStack-Helm. Okay, so the main agenda of this whole session is to show a OpenControl controller upgrade from one version to another version. Keeping that in mind, what we have done is we have already brought up a Control controller V1 cluster along with OpenStack-Helm, and we have deployed a heat stack, which basically created two virtual networks, left virtual network and right virtual network. And it also created a virtual firewall. So basically what we will do before we start the upgrade is we'll steer the traffic from right virtual machine to the left virtual machine and have the upgrade running. So let's go to the demo. So basically, this is how the topology looks like. So we have 3 virtual networks, right, left, and management. And virtual firewall has basically on all those 3 virtual networks. And we have a right virtual machine and left virtual machine. So basically, we'll start the ping from right virtual machine to the left virtual machine once we start the upgrade. Let me log into the Control web UI. And this is the V2 controller. Okay, I'm just adjusting few screens here. So what we are going to show is on the left-hand side is nothing but we are going to run the demo script. On the top right hand, what we will be doing is we'll be watching for the pods, like the Control controller V2 pods to be running, and on the down terminal, we'll be starting a ping from the right VM to left VM. So basically, in this demo, we have already installed the heat stack, which is basically doing a standard telco service chaining. And we'll be upgrading the Contrail from version 402 build 34 to 402 build 35. And we'll keep the ping running from right VM to left VM. So currently, we have a cluster with OpenStack-Helm charts and OpenControl charts which are already up and running. As you can see, these are the various OpenStack charts and also OpenControl charts as well. There are 2 charts which you can see which are deployed, which is OpenControl controller and OpenControl vRouter chart. Now let's see various pods which have been deployed using these charts. So there you go. So there are all the Contrail-related pods which have been up and running. This is the Contrail controller V1 pods. And then we have OpenStack-related pods which are up and running. So let's start the ping from left VM to right VM. Now let's see the nodes which are labeled as Control controller V2. So what we have done is there are a couple of nodes in this Kubernetes cluster, and we have labeled one of the node as Control controller V2, where the V2 ports will come up. And we already have the master node where we have Control controller V1 ports which are already running. So as you can see, 5B6S17 is labeled as opencontrol.org/controller V2. And we are going to deploy OpenControl controller v2 pods on it. So we'll use the helm install command to do it. So on the right-hand side, as you can see, we have put a watch on Control controller v2 pods. So every time if there is a change in the status of the pods, it will show at the end of the terminal. For example, there is a generate config job, which was in initialization state, and it went to the running state right now. So now let's go back to the slides. So what we have seen is it takes around 6 to 7 minutes. So we'll go back to the slides, and then we can come back and see the status of the upgrade. So as part of this upgrade requirement, we had a lot of dependencies, right? So we are running all those jobs which are needed for upgrade to complete. So we needed a way to resolve these dependencies, right? So what OpenStack-Helm provides is nothing but a framework where you can declare exactly the dependencies and how each pod should be instantiated. It could be a job, it could be a daemon set. So this is how we have resolved the dependencies. So the main requirement is that the control controller v2 to be running, and then, sorry, I forgot to use the flicker. Okay, so there you go. So basically, control controller v2 should be implemented, and then it will spin the generate config job. So the migrate config job will wait for the generate config to complete, because it needs a file which will be generated from the generate config job so that it could start the upgrade process. So here, update vrouter job, it basically waits for migrate config to complete, and once it is successfully completed, it will instantiate itself. And the final job is the finalize config. So it basically waits for all the above jobs to complete, and then it will instantiate itself. So this is how you can resolve dependencies. What we have done is we have just used daemon sets and jobs to resolve the dependencies. What you can also do is you can introduce something like services. So you can wait for some endpoints to come up, and then you can trigger some pods or deployments using OpenStack-Helm. So there are various jobs what we described in the previous slide. So let's go deep into it and see what exactly they are doing, right? So there is generate config. So what it knows is where the control controller v1 is running, and it also knows where the control controller v2 is running. So it goes into the control controller v1 cluster and gets all the information related to the Cassandra cluster and the Zookeeper cluster. And also it goes to the control controller v2 and gets all the information related to the Cassandra cluster v2 and Zookeeper cluster v2, which are running there. And it creates the configuration file which is needed by the next jobs like migrate config and finalize config to run. So that's what the ISSU gen config is doing. So here, config migrate. So this is a very important job. So basically what it does is it reads the configuration file which was generated by the gen config, and now it basically initializes connection to those Cassandra cluster and also Zookeeper cluster on v1, and also it initializes the connection to the v2 cluster as well, like similarly to the Cassandra database and the Zookeeper. And now it will start migrating the data from cluster v1 to cluster v2, both like the Zookeeper data and also the Cassandra data as well. So now, once the migrate is complete, so what we are doing with the update vrouter job is we are using this job to update the vrouter and say that now that the migration of the config DB data is complete, you need to point to the v2 cluster, and that's what we are doing using the update vrouter. So we are basically pointing it from v1 to v2. And this is the finalize config job. So now at this point of time, it's just doing a final merge from cluster v1 to cluster v2. Also, during this process, what has happened is it might have stopped many services on control cluster v2. So it will make sure that it will bring up all the inactive control processes, and it just verifies that everything is working fine. So this is how the upgrade works, and these are the different steps. Now going back to the upgrade which is happening in the background. as you can see, there were many jobs which were in 0/1. It means that it is not ready. So what we have done is there are a couple of readiness scripts which we are running in the background. It basically checks that all the services which are running in the Contrail containers are active. Once it is active, that's when it will declare that there is, okay, like the pod has come up. Otherwise, it will show it as not ready and will not be able to log in using the kubectl accept command. So there are various things which are happening there. So basically, as you can see, the generate config completed, and that's when the config migrate v2 started initializing. And now that the migrate v2 has completed, the update vrouter started initializing. And so the finalized config is also initializing. And on the below screen, you can see that the ping is already running. So here, using the finalized config, it will just do a final merge, and it will wait for the merge to complete. And once it is complete, we can verify the Contrail status on the Contrail controller v2. So yeah, so all these dependencies which are provided using OpenStack-Helm, and the way it provides to do readiness checks, like it could be any kind of health checks, right? You can say when, like we can basically have some script to say when the container, when the pod is ready, and also you can add liveliness scripts to basically check every 120 seconds, or it could be 60 seconds, to check whether whether the service is active. Okay, so we're just waiting for the Contrail ISSU finalized config to complete. So the interesting part of what we have achieved using OpenStack-Helm and its utilities is we used to do this upgrade of Contrail from one version to another version in like 30 to 35 minutes. And I think now we are able to do it persistently in like within around 6 to 8 minutes. So that's the power of what Kubernetes, Helm, and the whole OpenStack-Helm infra provides. So we're just waiting for the finalized config to complete. So it's basically completed. So now the finalized config is complete. It will bring up the inactive processes. And this is when the Contrail controller should show it itself as ready. And OK, here you go. So the Contrail controller is shown as ready. Let's check the Contrail controller status. So this is the Contrail controller v2, and we are going to check the Contrail status here. As you can see, all the Contrail processes are active. Now let's check the vrouter status. So as you can see, that vrouter is also active. And on the right-hand side, the ping is still on. So I'm going to cancel the pin. And we lost one packet there. It's pretty much like 0% packet loss, what we did here using this upgrade procedure. We'll go back to the web UI and see. I think it's fine there. So basically, all the data which were there in Contrail cluster v1 has been migrated to the v2 cluster. So this pretty much shows that the upgrade is done, and we have moved from build 34 to build 35 of 402. So yeah, that's it. That's the live demo we had.
So
we have few links to the OpenStack-Helm repository, and also for the blog and the treasure map.
to recap, Madhukar, in about 6 minutes,
Yep.
within a single OpenStack-Helm-based environment, you instantiated 2 separate versions of OpenContrail, and with essentially 0% loss, was able to transition the tenant traffic from one version to another.
Yep, that's right. And it was pretty much happening, everything was live. Yeah.
Very cool.
And also, this code is being merged upstream, so anyone can use it?
Yeah, so what we have done is we have upstreamed our patch set, and we are also working on getting that patch set through the CI/CD of OpenStack-Helm. And we are looking forward to getting it merged. And there are a few things which we are working on just to make sure that we kind of satisfy all the requirements of OpenStack-Helm as a community.
Very cool. Anyone looking to learn more about OpenStack-Helm, get a little bit more hands-on, ask any questions of Madhukar and the rest of the team, please come to the OpenStack-Helm workshop tomorrow. Thank you.
Thank you.